As water moves through plants, it first enters the roots and then moves through stems before it gets to leaves. Water moves through stems to replace water lost by transpiring leaves. So again, the soil-plant atmosphere continuum is a rope of water that goes from the soil through the roots, stems, leaves, and out into the atmosphere. And stems are in the middle of the roots and leaves. Thinking about how much water moves through the stem, again you have to think about the driving force, which is the water potential or the vapor pressure gradient, and the resistance. Now stems being in the middle of roots and leaves don't necessarily have a different driving force than a different part of the plant, but the resistances associated with stems can be important. The resistance of stem and water moving through those stems really has to do with the diameter of xylem vessels. Xylem is the part of the stem, they're dead cells, where water primarily moves. And those cells are the most important conduit for water going from roots, stems, and then into leaves. And there are differences in the resistances among different xylem elements. So this right here is a xylem cell, and this is another xylem cell. And these are long straws or long tubes that run when connected from the roots through the stems into the leaves. And what's important to know about xylem is that if you have a relatively small xylem diameter versus a large xylem diameter, these small versus large ones, these small xylem elements have a lot more resistance to them than a large one does. Quite simply, a small pipe has a lot more resistance than a large pipe. And even if you were to put together a bunch of small pipes that had the same total cross-sectional area as a large pipe, there's a lot more resistance here in the small pipe than there is the big pipe. So the bigger the pipe you have, the more water you can move through it, even proportional to the amount of area that it has. So you'd think that plants would want to have very large xylem, but there's a trade-off. Although it's efficient to move a lot of water through a very large pipe, and therefore you can conduct a lot of water. So large pipes might have very high conductivity or movement of water for a given amount of pressure or tension. But the trade-off is what's called cavitation. And if you remember, we tend to think about water as being a rope through the plant out the top. But what can happen though is that if this rope is a relatively thick rope and you have relatively large xylem, that there's a lot more of the opportunity for that rope to snap. And once that rope snaps, this water falls back down to the bottom, this water gets sucked out to the top, and it's really hard to make another rope of water that goes through the plant. The snapping of the rope is called cavitation, and essentially it's the introduction of air into xylem elements. And it turns out, without getting into too much detail, that the wider your xylem element, the more likely you are to have cavitation. The more likely air is to get into that water rope and snap it. As a consequence, there's a relationship between the water potential at which plants cavitate or lose all the ability to conduct water, and that's here on the x-axis, and the minimum water potential that we see in nature here on the y-axis. So if you look across a broad range of species, here's your one-to-one line, which means that a plant in nature might be at -9 megapascals for its water potential, and that's right at the point at which it starts to lose all ability to conduct water because you've had cavitation in all the xylem. And what most plants do is they're going to stay above that line. So their water potential is going to be a lot higher than the point at which you have cavitation. So this right here would be your margin of safety, for example. What's important with the safety margin is that for plants that aren't able to tolerate much water stress, there tends to be a much smaller absolute safety value than those plants here that can tolerate more water stress. Now, water transport, the total amount of water transport, depends on the quantity of conducting tissue. This example shows the relationship between the sapwood area of a tree and the leaf area of a tree. Now, sapwood, if you take a cross section of the trunk of a tree, sapwood is a conducting material within the tree, and not all of the material or the cross section of a tree can conduct water. Sometimes those xylem elements that normally conduct water become clogged up or filled with resins. And so you take a look at the sapwood area, which is a total area of wood that can conduct water up to the top of a tree, and compare that to leaf area. And usually what you have for a given species is a linear relationship between leaf area and sapwood area. And what this means is that there's a constant ratio between the amount of area to conduct water with and the amount of area to evaporate water and the amount of area to conduct water. But it differs among species. So Douglas fir tend to be in relatively mesic or wet places. And you can see that for a given amount of sapwood, you have a lot more leaf area for Douglas fir than you do ponderosa pine, which tend to be in drier areas. And the reason for that is primarily how the xylem are built. Douglas fir is going to have relatively large xylem, and ponderosa pine relatively narrow xylem. And so therefore, because the resistance is greater in a smaller diameter xylem than a larger diameter xylem, if you put all the smaller diameter xylem together, you're going to need a lot greater area of conducting xylem to support a given amount of leaf area in ponderosa pine than you do for Doug fir. Ponderosa pine has smaller vessels, smaller xylem elements, and therefore they support less leaf area per unit sapwood than does Doug fir, which tend to be on moister sites. So this just goes to show that the resistance to water movement through different plants is not the same across all of species. Most plants are not limited by the capacity of stems to move water. The limitation to water movement tends to be at a different part in the plant, or the interface between the plant and the environment. And it's not usually the capacity of stems to move water. Most plants make sure there's enough capacity to move water through the stems so that it doesn't become a limiting factor to water loss through the plant. Stems do more than just move water. In some cases, they also store water. And water storage in stems buffers the plant from imbalances in water supply and demand. This figure here shows the seasonal time course over a day. So there's 24 hours on the x-axis. And the y-axis is transpiration rate, the rate of water loss out the top of the plant. And in addition, they show water absorption. So in this case, we have a pool of water that might be inside the plant. And we're going to take a look at the time course of water being lost from the plant, that's transpiration, and water entering the plant, which is absorption. Now transpiration starts in this case relatively early in the morning, somewhere around 6, 5, and it goes up and up and up. In midday, transpiration is highest. And then it goes down. And some of this variability, for example, is going to be due to clouds passing over, changes in temperature and insolation on a short time scale. So that's the pattern of transpiration. That's the pattern of water loss. And if there is no storage within the plant, you would expect water absorption to be parallel transpiration exactly. But actually there's a delay, and water absorption happens later on average than transpiration. This is because there's storage of water in the plant. And this diurnal time course of water absorption and water loss by a tree in this case shows that storage of water serves to support water loss by the leaves that then gets refilled by absorption at a later point. Now stems can actually store a lot of water and more than just what's going to be used on a scale of just a couple hours. If you take a look at the amount of water that's stored in the stem of a tree, there could be 5 to 10 days worth of water stored in that stem of the tree. And in some cases, in deciduous areas, what you find is that plants will leaf out even before it starts to rain, or they'll produce flowers before it rains. And although it's still in a dry environment, they're able to persist on a weekly time scale with water that's just stored in the stem of the tree. Succulents, as you know, things like euphorbias and cacti and other plants, can persist on stored water for even longer. They can continue to photosynthesize it, albeit at a low rate, for months, sometimes years on end, without rain.